Okay, now the steady state error specifications. Actually, when we talk about the transit response, we highlight some of the parameters or performance metrics that we use to find in order to analyze the system performance in terms of transit response. For example, we talk about the damping ratio and the settling time, the peak time, and also the overshot. This for the second order system. Okay, and we say these specification are used in the control system for the transit response. The same thing in the steady state response or in steady state error analysis. Here we already mentioned that we have three main constants, which is the position constant, velocity constant kv, and also the acceleration constant, which is ka. This constant actually can be used as specification for the control system steady state errors. So from this constant uh, we can expect what will be the type of the system and how the system will behave. Okay, so for example here, if we have a control system with a specification of kv equal to 1000, that means you give you a system and they said the velocity constant is 1000. What are the information that we can get from this parameter or from this specification? If the system has a kV equal to 1000, that means the system is stable. Why? Because if the system is not stable, we cannot get a value for its steady state error parameters. Then the system is type 1. Why system type 1? Because the only system type 1 has a constant value of the velocity, which is finite or constant. Okay, so system type 0, I mean, if the system is type 0, the value of kV is 0. And if the system is type 1, I mean type 2, the value of the kV will be infinity. But our kV is 1000, that means our system is type 1. So see, from this specification, we know that our system is stable, our system is type 1. The next information that we get is a ramp input is the test signal. Why we use a ramp input? Because we said when we want to test the system which is related to the velocity, we need to use the ramp function. If it's related to the position, we are going to use the step function. If it's related to the acceleration, we are going to use the uh, parabola function. Okay, so since we have kv here, so our system or the test signal will be the ramp function which is used for our test. What else we can get? The steady state error. For this case, if you have the kv equal to 1000, that means the steady state error of this system, which is equal to 1 over kv, will see also a finite number, 1 over 1000. So it will be a finite number which equal to 1 over kv per unit of input slope. Okay, so these are the information that we can get from one specification for our system. So even you get the value of kv or the value of ka or the value of kp, all these parameter or all these specification will tell us some information about the behavior or the performance of our control system and the nature of the system. Okay, so we have this example here was for interpreting the steady state error specification. So what information is contained in the specification kb equal to 1000? Kb here is represent the position constant, and we said the position constant, which is kb, always use the test function of the step function. Okay, and the kb will get a value here because kb as a the formula of kb equal to limit s goes to 0 gs. So if I have kb with a constant value, that means my system is type 0. Why system type 0? Because I do not have any s in the denominator of the transfer function. If there is no s in the denominator, that means the kb will give you a constant value. Okay, so our system is stable, the system is type 0. What else? Because for also the system type 1 and system type 2, the value of kb will be infinity. Why infinity? Because if you have s in the denominator like this one, so if you have such s here, it will make the denominator of the transfer function equal to 0. Then whatever is the value here, it will be over 0, so it gives you infinity. So the kp will be infinity for the system type 1 and system type 2. For that, for sure, our system is type 0. Okay. Then the input test signal is the step function, as we said, because the step function is used to test the system or the application, which is based on the constant position. Then we have the value of the error, which equal to ESS here equal to 1 over 1 plus KP. So 1 over 1 plus 1000, it will give you this value, which is 1 over 1001. Okay. So this is how to use the specification of the steady state steady state error in order to identify the system type, the system stability situation, also the system values of the steady state error value. In this example, actually, we are going to design the gain to meet the steady state error specification. That means there is steady state error requirement. We need to design our system in order to meet this requirement. So, for example, here we have this system with the value of the gain k. We don't know what is the value of k here, but we need to find the value of k so that there is 10% error in the steady state. That means the value ESS will equal to 10%. Okay. Since the system is type 1 here, our system is type 1 because the highest is in the value of n equal to 1. The error stated in the problem here must apply to a ramp input. Why ramp input? Because system is type 1, so we go for ramp. We said type 0, we go for a step function. Type 1, we go for ramp function. Type 2, we go for parabola function. Okay, so since our system is type 1, so we are going to for the ramp function, which is equal to 1 over s squared. Okay, thus the value of the error here, which is 1 over kv, 1 over here, this value here of k, the k here is kv. Why kv? It's not kp, it's not ka, because we are talking about the system type 1. So system type 1 here we have the value of kv, here we have the value of kp, here we have the value of ka. Okay, so now we are here this part. So the steady state error will equal to 1 over kv. This is the formula from the table, which equal to 0.1 is given, which is 10% equal to 0.1. So the value of kv equal to 10, which give you the limit of, actually it's the value of kv here will equal to 10, and the value of 10 here, if I find the formula of kv will equal to limit s goes to 0 sgs. So this is the formula for finding kv. So I put kv equal to 10 on the left side, and on the right side I'm going to apply the formula limit s goes to 0 sgs. So s times, if I multiply this one by sgs, so s, this s will go with that s, so I still have k and s equal to 0, s equal to 0, so I have k 0 plus 5, so it will be 5k, okay, over, and I put here s equal to 0, so I have 6, s equal to 0, I have 7, s equal to 0, I have 8, so it will be 6 times 7 times 8, so it will be 6 times 7 times 8, this will be the value. By solving this equation, actually this is equal to 10 here, that means the value of k will equal to 672. Okay, you solve this one for k, you will find the value of the gain, which equal to 672, in order to achieve kv equal to 10 or error equal to 10%. Okay, So this is how to apply, I mean, how to use uh, the steady state specification in order to define or find the value of the gain. By applying graph table criterion, we will see that the system is stable at this gain. So if we substitute the value of k here, I replace this k by 672, and I write the transfer function 672 s plus 5 over s times s plus 6, s plus 7, s plus 8, and I find the closed loop transfer function. Then I go to find the characteristic equation and construct route table. So for sure our system will be stable here at this value of k, which is 672. The steady state error for non-unity feedback. Actually, our talk during the previous video all focus on the unity feedback, and it's the most common one here in order to simplify the calculation of the steady state parameter for the unity feedback. For that, if we do have a non-unity feedback like this one, that means they have HS here. So this gives you a non-unity feedback. So it's not easy to apply the formula that we have for ES, which said ES equal to RS over 1 plus GS. This will not be applicable anymore. So in order to make it applicable, we must convert our system from non-unity feedback into unity feedback. So if you have HS here, we are going to add -1 and +1. So we add two loops, or I mean two feedback in parallel, -1 and here is +1, correct? So this is +1, this is -1. So it's like we add 0, -1 plus +1. The total of these two is 0. So it's like we didn't add anything. Okay, you add one feedback -1, one feedback +1 to the same summing junction. The next step, you are going to combine HS with -1 because they are in parallel, for example, in order to keep our positive unity feedback here. So when I combine HS with -1 like we did in chapter 3 for the reduction techniques, so HS minus 1 give you this value here. Then this value with the GS can be considered as a feedback system, and it will give you this transfer function, while the unity feedback still here. This is the unity feedback or the value of 1. Okay, so now this method just used to convert from non-unity feedback into unity feedback system. Why? In order to simplify the calculation of steady state parameter based on the formula that we learned before, using the GS value, which is RS over 1 plus GS. So this is one example here, steady state error for non-unity feedback systems. So we have a non-unity feedback system here with a value of 1 over S plus 5. This represents the value of HS, and this one is represent the value of GS actually. So in order to find the system, we need to find the system type, the appropriate error constant associated with the system. That means we need to know what's the type of the constant. Is it KP, KA, KV, which is suitable for that system type, which is type 0 or type 1 or type 2, and the steady state error for the unit step input. He said here unit step input, that means he already tell you the input of our system will be 1 over S. Assume input and output units are the same. Okay, so here the input will be 1 over S. So after determining the system is indeed stable, after we confirm the system is stable, the first step for solving this problem is to convert the non-unity feedback into a unity feedback. Okay, so this will be the first step here, by converting our system from non-unity feedback into a unity feedback. Sorry, so we need to add one line for one line for -1. Okay, like we did in the previous example and the previous slide. So here, when we have 1 and -1, the -1 will be combined with the 1 over S plus 5. So this will give you the value of the I mean to combine the hs with -1, so it will be like hs minus -1. It will be like one block hs minus -1. So what is the value of hs here? It is 1 over s plus 5 minus 1. So it will give you like s plus 5, 1 minus s minus 5. So it will be like 1 or it will be like 4 minus s over s plus 5. Okay, so this will be hs minus 1. Then this transfer function actually, or this the feedback, will be combined with the original transfer function to give you the feedback transfer function. So as you can see here, gs equal to 100 over s plus 100 is the value of gs. hs equal to 1 over s plus 5. So in order to find the equivalent, it will be like gs over 1 plus gs hs minus gs. Okay, so we combine because we add -1 there. So the transfer function here will become 100 s plus 5 over s cubic plus 5s squared minus 50s minus 400. This after we apply the formula which said gs or g equivalent here equal to gs over 1 plus gs hs, but hs already here become hs minus 1. Okay, why minus 1? Because we add -1 and +1 in order to convert from non-unity feedback into a unity feedback. Okay, so this our equivalent transfer function. And for the unity feedback, what we can see here, the type of the system here is the system is type 0. Type 0 because we have one s in the denominator of our transfer function. And type 0 because we do not have any s in the denominator of our transfer function. Cannot have s alone here because we still have 400. So there is no s common between all the polynomials here. Since there are no pure integration, so the appropriate error constant function here will be kb. Okay, since the system is type 0, the appropriate constant will be kp, and the appropriate transfer function, input function, will be the step function as you mentioned in the question. So the value of kp here will equal to limit s goes to 0 g equivalent. So you just substitute for each s here by 0. This becomes 0, that one becomes 0, that one becomes 0. We have 100, this 0, 100 times 5, it is 500 over -4. So it gives you the value of kb, which equal to -4 over -5 over 4. Then in order to find the steady state error for this function, we find 1 over 1 plus kb. We substitute for the value of kb here. We got the error is -4. The negative value of steady state error here implies that the output step is larger than the input step. It means since you have error is -4, that means your output is larger than the input. Okay, so if for example if the set point is 10, you will get the output is 14, which is higher than the by 4. Okay, so this is how we can find the steady state error for the non-unity feedback system. So we need to apply this form: add +1 and -1, then combine h with the -1 and keep the +1 is there. We combine h with the -1, then we find the transfer function as a formula here: gs over 1 plus gs hs -gs. As you can see here, this formula is the formula to convert the non-unity feedback into unity feedback. If you want to convert the non-unity feedback to unity feedback, your transfer function will become gs over 1 plus gs hs minus gs. This is the formula that we see here. It is gs over 1 plus gs hs minus gs. You just substitute for the value of gs, the value of hs. You can find your unity feedback transfer function. Then you can apply the calculation to define the system type, to define the constant type, and to define the value of the steady state error. And now, at this point, we come to the end of chapter 4. Next, we are going to start with chapter 5 on the calculation of the system stability by using root lookups.